So we're going to continue with the copper experiment or the copper example that we were dealing with earlier section. Now that relates to reactions in sequence. Okay, for stoichiometric purposes, when the same substance forms in one reaction and reacts in the next, it is common to both reactions. We eliminate that substance in an overall, meaning net equation. The steps in writing the overall equation are: write the sequence of balanced equation and then adjust the equations arithmetically to cancel the common substances and add the adjusted equations together to obtain the overall balanced equation. Writing overall equation for a reaction sequence. In the previous problem that we dealt with, roasting is the first step in extracting copper from chalcocite, the ore used in the previous problem. In the next step, remember we made copper 1 oxide and sulfur dioxide. Copper 1 oxide react with powdered carbon to yield copper metal and carbon monoxide gas. We can write a balanced overall equation for the two-step process. So what we're going to do, we're going to write the individual balance equation for each step, and we're going to adjust the coefficients so that any common substances can be cancelled, and then adjust the equations together to obtain the overall equation like this. Now remember we did this one together, copper 1 sulfide with oxygen giving us copper oxide and sulfur dioxide. So the second step is the copper oxide that we formed in the first reaction going to react with carbon to form copper and carbon monoxide. So in the second reaction is when we make the copper, our desired product. And this is a reaction in sequence, meaning one of the first products that we made is going to use as a reactant. So in our overall reaction, we can cancel these two because it's a product here and this is a reactant. But in order to cancel, we need to have the same amounts. So there are two copper oxide here, so we need to multiply this whole equation by 2 after it's been balanced. Now let's see if it is balanced. There are two copper, it's balanced already. One carbon, one oxygen, one oxygen. Adjust the coefficient so that the 2 moles of copper oxide formed in reaction 1 are used up in the reaction 2. So we're going to balance this whole equation by 2. So this is the first reaction and this is the second one. You multiply it by 2. 2 copper 1 oxide, 2 carbon, 4 copper, 2 carbon monoxide. And now you can add these two together when you are adding. So this is a product, this is a reactant. So they can be cancelled. So overall reaction would be 2 copper sulfide, 3 oxygen from the first reaction and then 2 carbon from the second one, giving us 2 sulfur dioxide, 4 copper, 2 carbon monoxide. If the two reactions or two reactants or products happen to be in one side, when we are adding like that, you can add them together instead of cancelling. But here it happened to be in the opposite side, so then you can cancel them. Okay, that's how you write an overall reaction if it involves more than one reaction to get the final reaction. Okay, now we come to another important concept, limiting reactants. Okay, this is important when we are doing any experiment in the lab setup. Okay, so far we have assumed that reactants are present in the correct amounts to react completely. In reality, one reactant may limit the amount of product that can form. The limiting reactant will be completely used up in the reaction. The reactant that is not limiting is in excess. Some of this reactant will be left over. Okay, so in the previous examples, we assumed that all the reactants react to give you the desired product. But in reality, it's not like that. One of the reactant would be limiting because that is going to determine the amount of product is going to formed, and one of the reactant would be in excess. Okay, now let's look at this analogy with this example. Now we're going to make a perfect sundae. In order to make a perfect sundae, these are the ingredients we need. We need 2 scoops of ice cream, 12 ounce. We need 1 cherry, and you need a 50 milliliter syrup. Okay, you put the 2 scoops and then you put the 50 milliliter syrup, and with 1 cherry you can make a perfect sundae. Okay, that's how our reaction is going to take place. So this is our product, and these can be considered as our reactants. Now let's say we have these amounts of reactants given to us. We have 1, 2, 3, 4, 5, 6, 7, 8 scoops of ice cream. We have 6 cherries, and we have 100 milliliters of syrup. With the given ingredients, how many perfect sundaes can we make? You put 2 scoops, 50 milliliter, 1 cherry. 2 scoops, 50 milliliter, 1 cherry. And you're trying to make another sundae. We have 2 scoops, but we don't have syrup. Right? Of course, I can eat ice cream without anything, right? But that's not the case. We are looking at this as an experiment that we are doing, a real experiment in a lab, right? So who is the limiting reactant here? It's the syrup. Syrup is limiting. So we have only 2 portions of syrup. We can consider that as 2 moles. So if you consider this as 1 mole, okay, let me write that down. You can consider this as 2 moles ice cream, 1 mole cherry, and then you can consider this as 1 mole syrup to give you a 1 mole sundae. Okay, right now you have 2, 4, 6, 8 moles ice cream, 6 moles cherries, and 2 moles syrup, right? So the 2 moles syrup is a limiting reactant, so we make 2 moles product. So based on the limiting reactant number of moles, you're going to get the product number of moles, irrespective how much in excess the other 2 ingredients, your cherries and ice cream, are going to be. Whichever give you the lowest amount of number of moles, we will give you the number of moles of products that you can make, and these would be in excess. Did you get the concept? Yes. So if you are given a certain number of reactants, moles, and then the products, if you can find out the least number of moles present, that would be the same amount of moles that the product also going to form. Okay, that is the concept of the limiting reactant. So what is our limiting reactant in this case? It is the syrup. It's the limiting reactant. 2 moles of syrup, and we get 2 moles of the products. Okay, perfect. Next, chlorine trifluoride, extremely reactive substance, formed as a gas by the reaction of elemental chlorine, meaning elemental chlorine is Cl2 and fluorine plus F2. The molecular scene shows a representative portion of the reaction mixture before the reaction starts. Chlorine is green, fluorine is yellow. Find the limiting reactant. Chlorine and fluorine together gonna give us chlorine trifluoride, ClF3. Covalent compound, we use the prefixes ClF3. And this is the reaction. So how many chlorine molecules are there? Chlorine is the green one. 1, 2, 3. So there are 3 moles of chlorine. How many moles of fluorine are there? 1, 2, 3, 4, 5, 6. 6 moles of fluorine are there. I forgot something. I need to balance it before I do that. Let's see how we can balance it. Okay, let me start again. I forgot to balance it. Okay, let's go back and balance it. Okay, so we have chlorine plus fluorine giving us ClF3. So there are 2 chlorine on the left side, so you can put 2 right there, 2 ClF3. Now we have 6 fluorine, so you're going to put 3 right there. So 3 times 2 fluorine. Now it's balanced, okay? But according to the diagram, what do we have here? We have 3 moles of chlorine, and then we have 1, 2, 3, 4, 5, 6 moles fluorine. And it is asking what is the limiting reactant. Okay, now we're going to see according to the balanced equation what is the maximum amount of ClF3 that we can make based on the given amounts. Okay. Okay. Plan is write a balanced equation, which we did, and to determine the limiting reactant, find the number of molecules of the product that would form from the given numbers of molecules of each reactant. Again, we're going to use the molar ratios. The balanced equation is this. We balance it together. There are 3 molecules of chlorine, 6 molecules of fluorine depicted. Now, with the 3 molecules of chlorine, how many ClF3 can we form? In order to do that, we look at the molar ratio. That is 1 mole of chlorine gives you 2 moles of ClF3. So you start with 3 moles of chlorine and use the molar ratio from the balanced equation. 1 molecule of chlorine give you 2 molecules of ClF3. So 3 times 2 can give you 6 molecules of ClF3. And then we were given 6 molecules of fluorine. And then we use the molar ratio. Fluorine to ClF3 is 3 to 2. So 3 molecules of fluorine gives you 2 molecules of ClF3. So that will make it the number of molecules of ClF3 going to be 4. Okay. So when you get the number of moles of product like this, whichever gives you the lowest number of moles is going to be the product that you're going to make, and that reactant would end up being the limiting reactant. Since the given amount of fluorine can form less products, 4 fluorine, it is the limiting reactant, and chlorine would be in excess. Okay, so fluorine is the limiting reactant because it gives you less number of moles. That's how you find the limiting reactant, and then the amount that can you form from the stoichiometric calculations. In another preparation of ClF3, 0.750 moles of chlorine reacts with 3 moles of fluorine. Find the limiting reactant. Now the same reaction, but now we have different amounts of chlorine and fluorine. The amount of chlorine 0.750, amount of fluorine 3 moles. Okay, same balanced equation. We start with 0.750 moles chlorine, and the molar ratio 1 mole chlorine gives you 2 moles ClF3. 1.5 moles ClF3 that you can form, and then with 3 moles fluorine, ratio is 3 to 2. 3 moles fluorine to 2 moles ClF3. So 3 and 3 get cancelled, can form 2 moles ClF3. Now according to these given amounts, the lowest amount is going to be 1.50 moles ClF3. So in this case, the limiting reactant is chlorine because the given amount yields less ClF3. Okay. Okay. A fuel mixture used in the early days of rocketry consisted of two liquids. So we have hydrazine and nitrogen tetroxide, which ignites on contact to form nitrogen gas and water vapor. And we need to find out how many grams of nitrogen gas form when 100 grams of hydrazine and 200 grams of N2O4 are mixed. How do we do this one? First thing is, we need to write the balanced equation. Okay. Now let's see how to write the balanced equation. Our reactants are going to be hydrazine and N2O4. N2H4 plus N2O4 ignites to form nitrogen gas and water vapor. Nitrogen gas and water. So this is the reactants and the products, and we need to balance this. There are 4 nitrogens on the left side, so we can put to begin with, so there are 4 nitrogens, so you can put 2 right there. And then let's see how many hydrogens. So there are 4 hydrogens here, so you can put 2 right there. That made 2 oxygens, but we have here 4 oxygens. So we need to change it now, right? Because number of oxygens are not the same. So how do we correct it? So we need 4 oxygen. So now we're going to change it. Water. So let's put 4 right there. That will make it 4 oxygen, and on the left side we have 4 oxygen. But now we have 8 hydrogens. So since we have 8 hydrogens, you need to put 2 here. So 2 times 4 will make it 8. Now the nitrogen, we have 4 here, and then you have 2 here. So we have 6 nitrogen. To make 6 nitrogen, we need to change this to what number? 3. Now we have a balanced equation. Okay. That's how you balance it. Okay. Now what's it asking? How many grams of nitrogen? We need to find out the grams of nitrogen form when 100 gram, 1 into 10 to the power 2 grams means 100 gram of N2H4. And 2 into 10 to the power 2 is 200. So 200 gram N2O4 are mixed. So we are given these 2. So how do we find out the number of, how many grams of nitrogen gas form? We need this is a limiting reactant problem. With these 2 quantities, 100 and 200, we have to separately find out the number of moles of nitrogen gas produced. Whichever gives you the smallest one or the lowest yield would be the limiting reactant, and that is the amount of nitrogen gas that is going to be formed. Okay, so let's go ahead and try to solve this one now. Okay, so we can start with N2H4. I'm going to go ahead and write down the equation again here. We have 2 N2H4 plus N2O4 giving you 3 nitrogen plus 4 water. Now you can start with 100 gram of N2H4. So 100 grams N2H4. First thing, we need to convert it to number of moles in order to use the molar ratio. So you use 1 mole N2H4 is the molar mass of N2H4, which is 32.05 grams. Now we convert grams to moles, and then you use the molar ratio. N2H4, molar ratio between N2H4 and nitrogen, that is 2 to 3, right? So 2 moles N2H4 react to give you how many moles of nitrogen? 3 moles nitrogen. This will give you the number of moles of nitrogen that can be formed with 100 grams of N2H4, and that will be 4.68 moles nitrogen. Okay, that would be 4.68 moles nitrogen. And then similarly we can find out with the 200 grams of N2O4 what is the amount of nitrogen that we can form. So for N2O4 you start with 200 grams N2O4. Grams, first you need to convert to moles. 1 mole N2O4 is the molar mass of N2O4, which is 92.02 grams, and then the molar ratio N2O4 to nitrogen 1 to 3. Okay, so 1 mole N2O3 gives you 3 moles nitrogen. This will give you the number of moles of nitrogen that can be formed, and that is going to be 6.51 moles. Moles nitrogen. Now between these two, which one is going to be the limiting reactant? What do you think? We have 6.51 and also 4.68. Which one is the lowest? So 4.68 is the lowest amount, so that is going to be the limiting reactant. Okay, 4.68. No, sorry, not the 4.68 limiting reactant. 4.68 is the amount of number of moles of nitrogen that can be formed, so that makes the limiting reactant N2H4. Okay, N2H4 is a limiting reactant and only 4.68 moles of nitrogen can be produced. But we want to find out in mass. So you take that 4.68 grams, not grams, that was in moles, right? Did a little mistake. 4.68 moles nitrogen, and then you convert it into grams using the molar mass of nitrogen. 1 mole nitrogen is 14 times 2, 28 grams nitrogen. That will give you the mass of nitrogen that can be formed from 4.68 moles of nitrogen, that is 131 grams nitrogen. So the limiting reactant is N2H4. Limiting reactant because it gave you the fewest number of moles of nitrogen. Okay. Okay. Now the reaction yields. The theoretical yield is the amount of product calculated using the molar ratios from the balanced equation. Now, the actual yield is the amount of product actually obtained. Actual yield is usually less than the theoretical yield. Now, if you do a reaction in an experiment, or an experiment in the lab, you always want to make sure that you calculate the percent yield. Meaning, what is the percentage that you make? Is it 90%? Is it 10%, 50%, 60%, like that? Okay. Actual yield over theoretical yield times 100 will give us the percent yield. Now the theoretical yield, so from our previous example, we can consider 131 gram as the theoretical yield, meaning in theory, if there is no other side reactions or nothing happen, if the reaction goes to completion to 100% yield, this is in theory we should be making 131 gram of nitrogen. Now, in order to find this number 131 gram, did we have to do the experiment in the lab? No, we didn't. We just calculated by using the amount of reactant that we used. So, theoretical yield of a reaction we can calculate ahead of time knowing the starting amounts. Okay, but the actual yield we get it from doing an experiment in the lab. So normally, what do you think? Can a percent yield be more than 100%? Normally no, because actual yield is always going to be less than the theoretical yield because it can undergo some side reactions, some unwanted products can be formed. You can lose it while you are doing some work, during the experiment. So normally it's less than 100%, but in some cases it can be more than 100%. That is, if your product is not completely dried, if it made in a water medium. Okay, so those things can add to the actual yield some moisture, making it more than 100%. Okay. Effect of side reactions on yield of main product, which I talked about. If you have A plus B, what we want is the product C, but the side products can lower the actual yield. Okay, let's see with this example how we can find out the percent yield. Silicon carbide is made by reacting sand, silicon dioxide, with powdered carbon at high temperature. Carbon monoxide is also formed. What is the percent yield if 51.4 kilogram of silicon carbide is recovered from processing 100 kilogram of sand? First, we need to know how to write the balanced equation. So we have silicon carbide and we are given the formula for silicon carbide. Silicon carbide is made. So if silicon carbide is made, that is going to be one of your products. By reacting sand, so sand is a reactant, silicon dioxide, SiO2, with powdered carbon, C. At high temperature, carbon monoxide also formed. So SiC and carbon monoxide are the products. And let's see if this is balanced. We have one silicon, one carbon, 2 oxygen. Need to make it 2. Since it became 2 carbon monoxide, you have to put 2 right there. Always you want to make sure you balance the reaction. And also you can put the states. Carbon monoxide also formed. What is the percent yield if 51.4 kilogram of silicon carbide is recovered from processing 100 kilogram of sand? 100 kilogram. So 100 kilogram of SiO2 is used. We want to find out what is the percent yield if silicon carbide is recovered. So silicon carbide. So we need to find out the theoretical yield. If 51.4 kilogram is recovered, meaning, so this number is going to be your actual yield. So remember, the percent yield is going to be actual yield over theoretical yield. Yield times 100. The actual yield is given to us 51.4. We're going to find out the theoretical yield. Excuse me. How do we find the theoretical yield? You use the 100 kilogram silicon dioxide and see what's the maximum of silicon carbide that you can make. Okay. So let's go ahead and do that in this space. So we are given 100 kilogram. So you start with 100 kilogram SiO2. And then we can convert this to grams. 1 kilogram is 10 to the power 3 grams. And then we need to always convert it to moles, because we cannot do anything with grams. You always have to go to moles using the molar mass of SiO2. So molar mass of SiO2 is 60.09 grams is 1 mole SiO2. And then excuse me, you can stop here and then find out the number of moles and then use the molar ratio, or you can continue to go with the conversion. But because of the space, I'm going to go ahead and stop here. 1664 moles SiO2. And then you take that 1664 moles SiO2, and then you use the balance ratio to find out the molar ratio. 1 mole SiO2 react with 1 mole to give you 1 mole SiC, silicon carbide. Molar ratio 1 to 1. And then you use the molar mass of silicon carbide to find out the mass. So molar mass of silicon carbide is 40.10 gram. So this will give you mass of silicon carbide. And then you can convert this into kilograms. 10 to the power 3 grams is 1 kilogram. So if you convert it to kilograms, that would be 66.73 kilograms. That is the theoretical yield. And then the percent yield is going to be actual yield over theoretical. Actual yield is experiment amount, which was given to us 51.4 kilogram, and you divide it by theoretical yield, kilogram, times 100 will give us the percent yield, which is 77%. That is the percent yield. Okay. That concludes our chapter